This lesson is on solutions. Okay, so our learning objective is to calculate the number of solute particles, volume, or molarity of a solution. Essential knowledge is to learn that solutions, which are also called homogeneous mixtures, can be solid, liquid, or gases, and the macroscopic properties do not vary in the sample. If it's a heterogeneous mixture, the macroscopic properties depend upon the location in the mixture. So what's macroscopic mean? It means the properties that you can see. All right. Secondly, we're trying to figure out about how to calculate solution composition. Molarity is the most common method used. And the equation is molarity equals moles of solute over liters of solution. Solute is what you're dissolving into something, and the solution is the whole thing together. Right. We also want to be able to use particulate models for mixtures, to represent interactions between components, and to represent concentration of components. Okay. So basically we're drawing pictures and we're calculating. So, solutions. There are two types of mixtures. There's the heterogeneous mixture and the homogeneous mixture. Homogeneous mixture, they look the same throughout. As you can see, you're pretty much the same pattern keeps on presenting itself throughout the whole solution. If I took one part of the solution and the other, it'll look pretty much exactly the same. Heterogeneous, though, you notice how all that, the purple's up here, all the green's down there. Heterogeneous mixtures do not have to be the same throughout. They vary. The difference, this would be like the difference between salt water. Salt water looks and tastes the same throughout. Homogeneous mixture versus like a salad. If you have a salad, you might have a few tomatoes here, a lot of tomatoes on the other side, some lettuce here, so on and so forth. Okay. The process of dissolving to make these mixtures, specifically in water right now, is we have our salt crystal, our solid, we put it in the water, and the water starts coming over, and the positive portion of the water and the negative portion of the Cl or the Na, they attract each other. Okay. And they pull each other apart, and the water kind of gets up in there and causes it to dissolve. And as you can see over here, obviously this is the positive, that must be the Na that's over here. And there's water molecules surrounding it. And notice the orange part of this is facing toward that positive every single time. That's because water has a partially negative side and a partially positive side. The hydrogen side is positive, the oxygen side is negative. So the negative side is going toward the positive ion. Over here, where we have our negative Cl, you see the positive part of the hydrogen pointing toward that negative. So what ends up happening is they separate and they surround, and they kind of make little hydration shells around that so that the Na and the Cl are just floating around independently of each other in the water. And here you can see that particle orientation a little bit better. Okay, so you have your Cl, which is negative, your hydrogen in the water, which are partially positive, being connected, and the partially negative oxygen being further away. So in every single case, the positive is close to the negative. And over here, on this next other one, you have your positive Na, and your partially negative oxygen is what's close to the Na. And the partially positive hydrogen is further away. Right. So, in order to figure out what the concentration is or how much of this solute is dissolved in the substance, dissolved in a volume, and particularly, most of the time we use molarity, where molarity is a mole. How many moles are in a liter? How many moles are in a liter? So the next few questions are pretty basic. Use the formula to do it. So if I have 2.5 moles of NaOH and have half a liter, if I divide that out, I'll find out how many moles would be in a liter. 5. And the molarity would be 5 moles per liter. Okay. If I have 3.3 moles of KNO3 and 1.8 liters, when I divide those out, it lets me know how many moles are in 1 liter. And in this case, it's 1.8. Okay. All right. Down here, we don't have moles. So we have to take this 30 grams of NH3 and we've got to convert it to moles first by dividing by the molar mass. And we find we have 0.75 moles of this NaOH. So we have 0.75 moles over how many liters? Well, I don't have liters either, I have milliliters. In order to change milliliters to liters, we always divide by 1,000. Now that we know how many moles and how many liters, we divide that to find out how many moles are in 1 liter. We have 7.5 moles in 1 liter of this solution. Now we're going to calculate the moles. Okay. So, if we have 0.35 moles in 1 liter, and we want to know moles, and we have 1.7 liters of the stuff, if there's 0.35 moles in 1 liter, how much is there in 1.7 liters? Well, we do the math on that, and we find we have 0.60 moles to 2 sig figs of our NaOH. Okay? If our molarity, 1.25, which means there's 1.25 moles in 1 liter, is true, then we can find out how many moles are in 5 liters. And when we solve for that to 2 sig figs, we get 6.3 moles of NaOH. Okay. All right, now we need to calculate the mass of the solute in these solutions. Okay, so the mass is what we're finding. So if we have so in this case, if we have 0.5 moles in a liter, which is what molarity is, we can find the moles in 1 liter. Well, that should be obvious. If there's half a mole in a liter, how many is in a liter? Half a mole. Okay. And this is CaCl2. Now, if I want to find grams, I've got to convert that to grams by knowing there's 1 mole of CaCl2. Whoops, I just realized I didn't write the full thing here. I'm going too fast for my own good. CaCl2. And then I go to grams of CaCl2 by using the molar mass. Which ends up making this 55.49 grams of CaCl2. Now this only has 1 sig fig, so I'm going to round this to 1 sig fig, making this 60 grams of CaCl2. Okay. This one down here If we have 1.7 moles in a liter, which is what molarity means, then we can find out how many moles is in how many liters. In this case, 42 milliliters divided by 1,000 gives me 0.042 liters. So there's 1.7 in 1 liter. How much is there in that many liters? And in this case, we find that it is 0.0714 moles of this K2SO4 in that. So if we convert that to grams, by using molar mass and multiplying by the molar mass, we end up finding to 2 sig figs, because both these have 2 sig figs, that we have 12 grams of K2SO4.